that is growing. This is a growing quantity, right? So essentially what we have is a generalization of the linear solution into a non-linear form, which is specific for the LTV models. So we have taken an expression that arises in the linear approximation, and here we have the exact non-linear generalization of the same thing, right? Now, if we want an LTV model that will mimic a purely growing mode, then we have to set this quantity here, the D0. We have to set this quantity, which is equivalent to this one here. We have to set it to 0. What happens if we set this quantity to 0? Then the perturbation only has the generalized growing mode. And this happens only if the Big Bang time is simultaneous. If the Big Bang time is simultaneous, this means that our density perturbation will only have a growing mode, right? And this is this also happens in perturbation. Perturbations, the choice of the growing mode is to avoid the perturbation going to infinity near the Big Bang, because this is what would happen. Well, here, the nonlinear perturbation would not go to infinity, but would take very large values. That is what would happen if the Big Bang time is not simultaneous and we approach the Big Bang. If we approach the Big Bang, then JD blows up, tends to infinity, right? JD. And JG tends to 0, because the Big Bang time is when T equals TB. So this goes to 0, growing mode goes to 0, and JD goes to infinity. So this quantity will tend, because they appear with different signs here, delta will tend to the minus 1, which is very large. The perturbations have to be very small, 10 to the minus 6, 10 to the minus 4. So minus 1 is a huge number. So, but nevertheless, the important thing you have to see is that we already have an expression for our delta. And our delta can be written in such a way that it provides an exact generalization of the solution of the linear perturbation equation, right? So, and here we can identify a growing mode and a decaying mode. And this is, I published a very detailed paper on this. And now, near the Big Bang, so as you can see, near the Big Bang, the growing mode goes to 0 and the decaying mode goes to infinity. And so, near maximal expansion is the opposite. If we, near the Big Bang, the growing mode is 0 and the decaying mode is dominant, is infinite. Now, as the models evolve, what we can see is that the growing mode tends to an asymptotic non-zero value and the decaying mode goes to 0. Therefore, for late time evolution, the growing mode dominates over the decaying mode. So the decaying mode is only dominant at the early stages of the evolution. This is the same as in the linear solution. The linear solution happens the same thing. So here we are making a correspondence between an exact solution of Einstein equations and perturbations, right? So this is the interesting bit.
Here, what you can you just go back to that slide, please? Okay. You have written GJ. It goes to GS, no? JS.
Let me go back.
Yeah, in near max expansion or asymptotic time, GJ goes to JS. It means it is asymptotic.
Yeah, it doesn't blow up. It doesn't go to infinity. The growing mode asymptotically does not go to infinity, but it rather goes into an asymptotic terminal value.
That means it will remain some constant, no? Because now
Yeah.
means like constant.
Yeah, it will tend to a constant.
Yeah.
But a non-zero constant.
Yeah, non-zero
Yeah.
constant.
But the other one will tend to zero. So which dominates?
Okay.
You know, 1 dominates over 0.
Okay.
3 dominates over 0. Right? So what I'm saying is that asymptotically, the growing mode will dominate over the decaying mode. But for early times, the decaying mode dominates over the growing mode. And this is the same behavior as in the linear case, right? Except that this is a non-linear expression. Now this becomes linear if here this allows you to define what are linear conditions in an LTV model. Linear conditions occur when this quantity is very small. And you can show that this quantity is very small only in early times. This quantity is very small, not at the, if the decaying mode is 0, then this quantity will also be very small near the Big Bang, right? But, in fact, this is very small near the Big Bang. In early cosmic times, this is very small. But it does not stay small all the time, right? It starts growing. So the linear regime in an LTV model doesn't last very long, and it has to be put in early times, right? And of course, if the decaying mode is non-zero, then you cannot have a well-defined linear limit very, very near the Big Bang. Because near the Big Bang, the decaying mode decays. But if you want to keep a decaying mode, then your linear regime has to be defined in these time ranges. Not in these ones, but in these ones. Anyway, these equations give you the conditions on how to define a linear regime in an LTV model. All what I would like you to see is that there is a connection with perturbation theory. There is a connection, but now LTV models are not perturbations, are exact models. But there are exact models that also mimic perturbations. In fact, they generalize the dust perturbations. They provide a generalization that is exact, that is non-linear and exact. And I think that we can, we should go for tea now.
Can you just give me the reference that you told us?
Yeah, it's a paper of mine in 2013, and it's called something like invariant characterization of the growing and decaying density modes. Characterization of the growing and decaying modes of LTV models. You'll see, you'll recognize that. It's a very large paper, but unfortunately that was an extremely large paper, very detailed and so on. But that's the nitty-gritty of this paper is what I'm saying.
Yeah,
The essence of this paper is that we can generalize the decaying and growing mode of linear perturbations in an exact form. Okay. Now the next, after lunch, what we're going to, after tea break, we're going to see how you can construct dynamical systems, say with the LTV models, so you see the phase space plots and everything. And I think that I'll do this very quickly, and I will skip the rest of the talk, the rest of the of this part, and we'll see the Sequer's models at least in the last part of the course, right? I think we've had enough of LTV models. We're going now to see Sequer's models. Okay, so let's have some. Let's have lunch. System. So since we have differential equations that look like ordinary differential equations, they are partial. That's as I showed. If the system was ordinary differential equations, then integration, then the initial conditions are given by constants. It is the initial conditions that are, not the equations themselves. Equations are not constant. They depend on time, the variables. But if the system was a system of ordinary differential equations, then the constant in the initial conditions are constant. But the dynamical equations are PDEs. They are not ODEs. They are PDEs, but they're PDEs in which only time derivatives are involved. Therefore, they can be treated as if they were ordinary differential equations in which the initial conditions are no longer constant, that they depend on one parameter. They depend on radius. See, the radial dependence in these equations is brought in at the level of initial conditions. Okay, so this means that we can look at the models as dynamical systems. We have to change the variables in order to describe it as a dynamical system, and we can use this. We change the quasi-local the equations for the Q scalars. We change them in this form. See, in this form, it depends on the density, curvature fluctuation, and the omega Q scalar. Okay, we transform them like this. Why like this? Well, it was trial and error. This is the one that gets a very nice description, and these are. Notice that we are able to eliminate. Sorry, we're able to eliminate one of the equations. So we have really three equations. The phase space. This is lambda equals 0. The phase space is three-dimensional. If lambda is different from 0, then the phase space is four-dimensional, and it's more difficult to understand. Now, so the models will be, sorry, the models can be studied as trajectories in this three-dimensional space. This is what dynamical, are people familiar with dynamical systems?
Yes, yes.
Yes? Okay. So, this is a dynamical system we have. See, here, essentially, the result, using these variables, is that the models have a past attractor here. This past attractor is the Big Bang singularity. See, that is that whatever you do, if you go into the past, you will find the Big Bang. There is no escape from that. All these models, if you go backwards, you find this attractor. This is a past attractor. It's a stable attractor. And all the models begin here. Then, depending on the initial conditions, very near the Big Bang, all the models behave very similar. There is no difference between them. Very near the Big Bang, all models, all LTV models are very similar. Well, of course, this is if the decaying mode is non-zero. As I will show you, models can behave differently if the decaying mode is 0. But in general, if the decaying mode is non-zero, all models begin here. And as they evolve, then initial conditions are important, because if here, what we can see is that if the dust layers expand perpetually, then the models go to a future attractor, which can be identified with Minkowski space. This is infinite future. This is so models with negative or 0 special curvature, they follow this evolution, right? This is a saddle point. They approach this saddle point, and then they go to asymptotic infinity here. Now, if the models collapse, then they do a different evolution. There's a bifurcation here, and then these curves go to infinity, and that means that they collapse. But I'll show you better pictures. Now, here we have the line of future attractors for models that are layers that are expanding. The Big Bang is a past attractor, and the expanding layers are these ones, and collapsing layers are these ones. Now we'll see some nicer picture. There we can identify an FLRW subspace. See, all FLRW models are located inside of this line. Now, let's see a better picture. Since we have already defined these quantities, JG and the growing and decaying mode, we can use these quantities as coordinates of the phase space. This is interesting because then we can see what happens when one mode dominates over the other. You know that these modes are exact quantities that generalize the density modes that we find in linear theory. Now, let's say hyperbolic models in which this is a study, and this was published. Here you have the reference in the Los Alamos archive. This has been already published. In fact, it's in the reference that. See, this is what happens with hyperbolic models in which both modes, the growing and decaying mode, is different from zero. These models begin at the Big Bang. This is a past attractor, and they have this trajectory. This is the FLRW subspace. They start very, very far away from FLRW, very far away. This is the Einstein de Sitter subspace, and then they evolve. They approach. This is a saddle for them, and they approach this subspace. That is, they homogenize, and then they end up in the Milne subspace. Anyway, these are, you can study the models as trajectories. It's a lot of detail here. The only thing I would like you to keep in mind is that the models can be described, the evolution of the models can be described as a dynamical system with attractors and saddles and everything. This is for the models in which the radial density profile has the form of a void. This is if you want to describe an underdensity with the models, then the dust layers will have this evolution. And this is very similar, but here in the case when the density profile is over an over density. It's very similar evolution. These are hyperbolic models with negative special curvature. Now, another point is hyperbolic models with zero decaying mode. This is what happens when the decaying mode is zero. When the decaying mode is zero, all the evolution of the models is concentrated in this plane. And as you can see, the evolution of the models is very similar to FLRW models. The other ones, the evolution started here, very far away from the FLRW regime. But when the decaying mode is zero, then the models are practically undistinguishable from FLRW in the early stages of the evolution. The evolution now starts here. This is a spatially flat FLRW model. See, the evolution is almost indistinguishable, and then they start to diverge from an FLRW model in the asymptotical time range. And then they are, Milne is a subset of Minkowski spacetime. So what happens with these models is that when at the Big Bang, they are very similar to FLRW. Then they expand and they start being very different from an FLRW model. And the end product, asymptotically in time they tend to Minkowski, okay, to Minkowski spacetime. And this is the same, this is for the void profile and for a clump profile. They are very, very close to FLRW at the beginning, and then they move away. So this is and the fact that the decay mode is zero means that all the evolution is concentrated here. This is a restriction of the dynamical space of the models. And elliptic models. Elliptic models are the ones that recollapse. So what happens when they recollapse? When they recollapse, this is the Big Bang, and it's a past attractor. Then they reach maximal expansion, right? And then they collapse to to the big crunch. The big crunch is the attractor, and well, it's a very simple evolution. They expand, reach maximal expansion, and collapse. And the future attractor is a big crunch. The past attractor is a big bang. This is when both modes, growing and decaying, are different from zero. And this is what happens when you have recollapsing models, but with the decaying mode suppressed, zero decaying mode. Then this whole evolution, that you remember it was something like this, now it is restricted to take place in this plane. All the evolution takes place in this plane, but it's very similar. It starts with a specially flat, very near specially flat FLRW, then it becomes very different, and then it collapses into this future attractor. So this is what happens when, okay, I'm going to stop here the LTV models because I need time to see Sekker's models. Okay, so there are many other things we can explore about the models using these variables. I think that you've already understood that these Q-scalars are very useful. They allow us to understand a lot of quantities, properties, and so on. They're also useful for practical calculations, but people don't, they still use the old variables and so on. But okay, now let's see something different now, Sekker's models. So far, we've been dealing with spherical symmetry. Now, this file, the Sekker is 7, the course 7, I've already given to Sushant, I think. Now I'm going to, this one, the number 8, it's the one we're going to see now. No, this is the 7, we're going to see the number 8. Yeah. Where is it? Ah, it's here. Okay. Conclusions. No. We don't start with conclusions.
Computer is also tired, actually.
Yeah, I think. Well, this is the last bit. And, okay, same thing. Now, we're going to see Sekker's models, only one lecture. We're going to see the following things about Sekker's models. They are no longer spherically symmetric, but also they are not the most general models at hand. What they do is that they impose a dipole. See, spherically symmetric distribution is a monopole, right? Dipole is when you have a direction, right? Okay, now if you superpose a monopole with a dipole, but you allow the dipole to move around, then things can get very interesting. So, but this is essentially what Sekker's models do. They introduce a dipole correction to spherical symmetry, but this is sufficient to get a lot of things done. Because spherical symmetry is very restrained, very constrained. Okay, so this talk is based on 2 papers. If you see here the reference, this paper has been published. This is say to appear, but has already been published. In this archive numbers, if you go Google this, it will send you directly to the paper. But this is an electronic print archive. If you go to, it is the Los Alamos National Laboratory, LANL, and then the archives, and then you can look at me in the search machine, and you will see these papers, but otherwise you can Google this thing, and it will send you directly to the paper, right? And Ismael Delgado Gaspar is my PhD student. So these 2 papers are part of his PhD thesis. And in fact, his collaboration, he did all the numerical work. And also, but he's not a compute person. He also understands things. So he's a very bright student, and this is a theoretical paper. It explains all the, it's very formal mathematical. This is more concise and applied paper. This is like an application of this one, right? This was submitted to JCAP, now it has been accepted by JCAP, so should appear very soon also, okay? So it's based on 2 papers where I'm going to talk about. Further details, you can find them in these 2 papers. Okay, so now, exact solutions of function equations that could be useful in cosmology. People normally think that all exact solutions that are useful in cosmology are too simple and too idealized. This is a common wisdom. And in fact, when people say that, they're thinking of spherical symmetry. We've been seeing LTV models, which are spherically symmetric. And what's the problem with these models? The problem is that we see these. This is, for example, a supercluster, reconstruction of a supercluster from a catalog, right? There are points here are galaxies. So we've put all these points together, and we try to record, but this is a cosmic structure that we see, right? So if we think of spherically symmetric LTV models, what we are doing is that we are modeling this by this, right? So it's very gross, right? It can give you information. It's not useless. It gives you information, right? So suppose you want to write the distribution of all the houses in Delhi, and you say it's a spherical distribution. It's not very realistic, right? But it can still give you some information, okay? So that's a big problem. How do we go beyond that? So it is evident that cosmic structure is not spherically symmetric. What we see there, over there in the skies, in the surveys, in the catalogs, is not a spherically symmetric distribution, right? So see, for example, this is a catalog. This is a catalog. We are here, and we reconstruct the structures that we see, and we see very large concentrations, the Sloan wall. This is a very large concentration of matter. Each point is a galaxy, each dot is a galaxy, so these are millions of galaxies, right? It's difficult to obtain this information because all what we see is 2-dimensional, so we have to add depth to that. And there are errors because we're dealing with objects that are very far away. And numerical simulations, these are numerical simulations. Numerical simulations, they take millions of particles and let them interact. And they interact, and they form, and these numerical simulations are expected, and they do show us how the structures that we see form. Of course, numerical simulations are not experiments. That's a mistaken thing. They're not observations, they're not experiments, because all the numerical simulations depend on the assumptions. What if the assumptions are not correct? How do you check they are correct? It's not so easy. But numerical simulations, they do show us a pattern of this type of filaments. This is called the cosmic web. These are overdensities of dark matter. This is dark matter, not visible matter, right? This is visible matter on the other hand. But what we do is that we assume that wherever there are concentrations of dark matter, visible matter clusters around them. So visible matter is a good tracer for dark matter as well. Sometimes there is what astrophysicists call the biasing factor, because we don't know exactly the percentage. If we have a blob here that is detected by gravitational lensing, then because of all the light we get, we can transform the amount of light into the amount of visible matter. And the lensing will tell us the proportion that this dark matter has with respect to the total matter that is there. And normally the results are that there are between 10 and 20 times more dark matter than visible matter. So visible matter is a good tracer for dark matter. See? And numerical simulations gives us more or less an estimation of the distribution of dark matter. And notice that these patterns, if you take this section and you look at one of these areas here, you see that there is very similar. There is a sort of filamentary structure that is surrounding other dense regions, or voids, we call them voids. And this is based on millions of galaxies, and the numerical simulations involve millions of particles. Okay? So this is what we would like to describe, and this is obviously natural. Right? Okay, so this is a reconstruction of the density contrast. In the cube, we are in the center of the cube. This is a local supercluster, we're here. And this is the density, the areas of high density contrast. This is a reconstruction of our cosmography up to 200 megaparsecs, 600 million light years. This is a reconstruction because if we make observations, we get only redshifts, and there are lots of errors, and we don't have very precise observations that reach so far. But we can reconstruct, we can take different bits of information and get this reconstruction. This is a very nice paper. It's published, it's called The Cosmography of the Local Universe. This is a reference, the Astronomical Journal. So we'd like to be able, obviously an LTV model cannot model this. Maybe we can say that an LTV model could be a model of this, provided we forget about the rest. Or the LTV model can be a sort of extremely crude average description of all this. But it would be nice if we could go beyond spherical symmetry, right? This is another thing. This is another description. This is seen from the sky. Now, the people who have done this work is Dooley, Courtois, Hoffman, and Pomeray. You can see it here. They have a beautiful video. You take this reference, you Google this. They have a very, very nice video, which they explain to you how they do these reconstructions. Okay, and also, very nice thing is that they have actually discovered that, because we don't know that there is a galaxy. Now you have 50 galaxies, they form a cluster. How we know they are a cluster? Because their velocities, I'm not on four velocities, they're three-dimensional velocities, they point out to common motion around the center of mass. That's why we know they are gravitationally bound, and they make a cluster. These are 50 galaxies. Now if you take 50 clusters, you have like a supercluster. So is there a larger structure? Because we can have cluster, supercluster, supercluster, supercluster. So where does it end? And it's difficult to know, because the larger the structure, the further away they are, and it's the more difficult to identify a common center of mass, right? So far, what these people have shown is that there is a supercluster, okay? And they call it the Laniakea cluster, which is so far is the largest gravitationally bound structure that we know, and it is about 200, 300 megaparsecs. Right? This is, so again, this is what we would like to be able to describe. See, this is a video. You can see it there. It's a very nice video with very nice music. It lasts about 20 minutes. I recommend you to watch it. Okay, so can we hope to provide a decent, at least coarse-grained description of cosmic structure of this type with an exact solution of Einstein equations? That's what I mean by coarse-grained. If I coarse-grain you, I substitute each one of you by a cube. Of course, they are not cubes. You're going to say, no, 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 I have ears, I have legs, arms. I'm not a cube or a cylinder. But coarse graining means to omit details. I want to omit details, right? So coarse grained description, a coarse grained description of all of you would be like not missing your individuality, but removing details from you. You would be described as, let's say, as cylinders.
Yeah,
or as cubes, elongated cubes, right? This would be coarse graining the description of all of you. So, but it's easier than to describe each one of you, including fingers and mouth and nose and everything, okay? So, can we, if you notice, all this description have a lot of detail, right? But maybe if I can provide a description that omits detail, but still keeps the basic with an exact solution of Einstein equation? Yes, Zacharias models. Yes, we can. We can with Zacharias models. You can do that. That's quite impressive for an exact solution of Einstein equations. Okay? So, why Zacharias models? Well, they are the most general, or rather less idealized, a class of exact solutions, and I put exact in quotation marks because in practice you end up doing numerical work as well, right? But suitable to cosmology. Right? There are other exact solutions in the world, but they are unsuitable for cosmology, right? And the Zacharias solution is quite general. For example, they admit much more degrees of freedom than LTV models. They have much more degrees of freedom. They do not admit isometries. There are no killing vectors. No, in fact, if you have spherical symmetry and then Zacharias. Now, Zacharias models contain a subcase that is axially symmetric. Now, axially symmetric is an isometry group of one dimensions. It's a one-dimensional. Remember, the spherical symmetry, the group is three-dimensional, but the orbits are two-dimensional, right? Now, axial symmetry, the group is one-dimensional and the orbits are one-dimensional, right? So, and this is already a generalization of LTV. See, so Zacharias model contain an axially symmetric generalization of LTV, but they have, in general, Zacharias models will not admit a single killing vector. And so, since they don't admit isometries, they're good candidate spacetimes to take all sorts of theoretical issues, not necessarily related to observations or cosmology. We can use these models to look at averaging, nonlinear perturbation, gravitational entropy, many, many problems. Okay? So Zacharias models are very useful. And also, all what I mentioned about FLRW models is applicable to them. There is one way to extend everything we have done on Zacharias models, on LTV models, to Zacharias models, except that it is more complicated. But the principles are the same. There is the fluctuations. The Q-scalars in Zacharias models can also be defined, but they depend only, the Q-scalars will be independent of the angular. They will remain spherically symmetric. But the fluctuations now will depend on all the coordinates. But we can define in a very similar way the Q-scalars and fluctuations. So a lot of work done with LTV models can be directly generalized to Zacharias models. Okay? So, see, this is the metric of the models. The metric of the models is now non-diagonal. And it's horrible. The metric in spherical coordinates, the metric looks horrible. It's absolutely, I'm not writing it completely. What you can say is that W, W1, W2, and W3 are horrible functions that depend on the three coordinates. Now you can see, you can recognize here LTV models. What happens if W is 0? If all these W functions are 0, then we get back the LTV metric. But since this is not LTV, all these functions are non-zero. They're not so horrible, actually. But they are, if I would write them in full, the metric would reach, it would be very long. So then it's not important. All you need to know is that these functions, see, in LTV models, all the metric functions depend only on T and R. Here, your metric functions depend on T, R, theta, and phi.
Because it's not spherical.
It's not spherical. Okay. So, oh, sorry. So when this thing happens, this finger moves on its own. Now, this function W is very important, because this function W that appears here is what is called the Seker's dipole. And it contains three arbitrary functions of R. And then has these quantities here. Now, why is this important? Because it is important because W is a linear combination of the three spherical harmonics. See, if the spherical harmonics, the real spherical harmonics, the J0, and here's why you have this confusion with Bessel functions. Hi. Don't sleep, don't sleep. Okay. I understand. We're all tired. This is fun. This lecture fun is the last one. Now, this is spherical harmonics. And this, the zero spherical harmonic is a sphere, is a monopole. The following three in the spherical harmonic surface, the spherical harmonic decomposition, these three are what are identified as the dipole terms, right, in spherical harmonics. And so this W is a linear combination of these three objects, which are vectors in Hilbert space. See? Well, you familiar with that, Hilbert space? Yes. Yeah. Okay. In Hilbert space, the spherical harmonics are a basis for Hilbert space, right? And it's an infinite dimensional space. But the three-dimensional subset of this space is a vector, and is a vector space. And this vector space is generated by these three basis vectors in the space of harmonic spheres. And this W, which appears here, is actually a dipole. It's a vector in this vector space. So they are rigorously, they satisfy this inner product law. That is, if we integrate these things, we can show that these are orthonormal spaces in this Hilbert subset of Hilbert space, and therefore we can identify these parameters here as the projection of the vector dipole into this in this basis, right? So rigorously, Seker's models define a dipole. A dipole where? In the space of functions, in Hilbert space, right? So, okay, so now, okay, we notice that all relevant geometric quantities depend on this function. See, this function is essentially telling us the deviation from spherical symmetry. But let's look at, these are the rest mass density has this form. Spatial curvature has this form. Hubble expansion has this form. Here, the shear eigenvalue has this form, and the Weyl invariant psi 2 has this form. Now, what happens when W is 0? we obtain the LTV forms. And the difference, the deviation from LTV is completely controlled by W. W is telling us, notice that W does not depend on time, right? W is, once you choose the three parameters, you choose the orientation of the dipole. And of course, this orientation will be changing as the second, because, well, we'll see that. But then the point is that W controls the deviation from spherical symmetry, and it is a dipole deviation. Now, spherical symmetry, Sekera's models contain LTV. So they contain spherical symmetry, but they deform spherical symmetry by adding a dipole. This is what they do, okay? We'll see this further. Here, as you can see, again, the dipole, the W, which appears here everywhere. This controls to what degree these scalars, there were other metric functions, W1, W3, but these metric functions don't appear here. Only one metric function appears here in the covariant scalars, and is W. That's why W is an important function. The other metric functions are not important. See? So we have 5 free parameters. The same 2 parameters that we have for LTV models. These are the essential parameters. These are initial average density and special curvature. And we have these 3 extra parameters. So before, this is the degrees of freedom that we had with LTV models, 2 free parameters. Now, for Sekera's models, we have 5 free parameters. So the space of initial conditions, it's much more increased. And also, when you set initial conditions, you have to set them in an initial time surface, right? In an initial time surface, all functions in LTV becomes functions of R. But here, for these models, initial surface of constant time will depend on R, theta, and phi. Therefore, the subset of initial points will be 3-dimensional, not 1-dimensional. Okay. So, invariant characterization of the models. See, we've seen that Petrov type D models, which are the models that we've called Coulombian fields, the zero magnetic Weyl tensor, and fluid source that is an irrotational geodesic 4-velocity. 4-velocity has no vorticity and has no acceleration, right? Therefore, it is a geodesic field, and it only has expansion and shear. These quantities can be computed from covariant derivatives of 4-velocity, right? Now, there is this thing, the local rotational symmetry, which means that these models of this type are more general than the ones I've been discussing. They are characterized by, we take a normal tetrad so that the metric can be expressed in this form, where this is a Minkowski metric, and we take the zero vector of this tetrad to be the 4-velocity, then we can, for these models, there exists a privileged space-like direction that serves as axis for, see, we have 4 tetrad vectors. One of them will be the 4-velocity, so we have 3 of them. What this is telling you is that out of the 3, there is a unique, we can choose one of them to define a rotation axis where the 2 of them can rotate, right? Do you see the point? You have 3 vectors. Now, you can choose one of them can be chosen so that the others can be rotated, right? So, well, that is always possible. But the question is there something that is preserved by this rotation? This is what gives us the invariance, right? And we rotate the other 2 vectors around this third one, and what we see, this is a picture, right? This is a picture. See? We have 3 vectors, and we choose one of them, E1, so that we can rotate the other one. These are small rotations, they're local rotations, right? Okay, this is the picture. Okay. This is not the spherical symmetry would be rotations around the whole sphere. These are just rotations around one axis, right? Okay. Now, what is preserved in these rotations is the following. In spherical symmetry, all spherically symmetric models satisfy this constraint. But what is preserved is that all curvature and kinematic tensors are invariant under this rotation. That is, if we do this rotation, we can see that the Riemann tensor remains the same. It's invariant under this rotation. The shear tensor is invariant under it. Weil tensor is invariant. All tensors, all kinematic and curvature tensors are invariant under this type of rotation. And in spherical symmetry is understood because this rotation is going to take place in the orbit. This is the orbit of spherical symmetry. So this small rotation will take place entirely in the orbit. And this is why spherically symmetric models are also LRS. But there are LRS models that are not spherically symmetric. They are more abstract, harder to define. Now, what happens in Sekker's models is that only the Weil and shear tensor are invariant under this rotation. The Riemann and Ricci tensors are not invariant under this rotation. So what we can characterize Sekker's models as being partially locally rotationally symmetric. This is one way to characterize them in terms of this rotation.
1 minute. If you will just move this circle or point from
To
here
another area?
Yeah.
No, it doesn't matter
It
because
doesn't matter.
no, because this triad is defined at every point.
Yeah.
Okay. Okay. This is very mathematically, very mathematical. Now, so far we have the following hierarchy of metrics. On top, we have seconds, right? It's non-spherical in homogeneity, right? We have seconds, right? This is the top hierarchy, the big boss, the top predator, the alpha predator here, the tiger, right? Now, below the tiger, we have the leopard. It's a small cat. Still big, but small. So this, if we set all these functions to 0, this reduces to LTV, right? So this is the leopard. Now, following, here we have the house cat. We call it wild cat, right? The small cat, right? You can do the same with like the wolf, the dog, and the French poodle. Okay, so if we remove if gamma equals 1, etc., then we get FLRW. So we have this hierarchy of models, right? So far we've been looking at these two, but now let's see a little bit more information about the big predator, the apex predator of the ecological space of cosmological models. Right? The top predator we're going to see now. Okay. Now, dynamics, we've seen this, you know, the 1 plus 3 formalism, the covariant objects you can define from it. Yeah, okay. Now, Einstein equations reduced to the 1 plus 3 equations, the constraints, we've seen all these. In fact, this is designed for people who have not seen this. So I explained. Now, here, we identify these two equations are essentially the FLRW subset, right? See? This is the same as for LTV. LTV satisfies these equations. So how do we? And then this is the subset. The FLRW subset is this, and this is the same with LTV. So how do we distinguish from these equations the LTV and Sekker's? From the constraints. The constraints, integrating these constraints, or spherical symmetry is not sufficient for sectors, because in the case of sectors, these are partial derivative equations with respect to spatial coordinates, right? These ones. These reduced to time derivatives. These are partial derivatives with respect to spatial coordinates. But since sectors depends on all the spatial coordinates, these will be partial derivative equations on all the coordinates. So solving them will give us the sector solution, which will generalize the LTV models. So this is the same, but the constraints are the ones that make the difference with sectorless models. Now, we define again the Q scalars can be defined exactly the same way. Yeah, okay. Q scalars are defined exactly the same way. However, there is an interesting thing. Every scalar, every covariant scalar in sectors is expressible as the sum of a spherically symmetric part and a part that contains the angular variables. But what we can show is that if we take this average, the way we have defined it, on this, what we can show is that the average of this part goes to 0. That's an interesting thing. We decomposed the scalars into a monopole term plus a dipole. This decomposition is not unique, but it is possible for every scalar. But what we can show is that once we take the average of the non-spherical part goes to 0. It's hard to believe, but it's true. In fact, this was discovered by my colleague Boleiko in 2007. The implication, say, all spherically symmetric, that is, all Q scalars we construct with sectors models will be spherically symmetric. The Q scalars in sectors models do not depend on the angular variables. There are sectors objects that do not depend on the angular variables. So they are identical to the LTV Q scalars. So we can say that every LTV model is an average sectors model. As you take sectors models and you average, you obtain the LTV model. LTV models are average sectors models. When you average, you remove local information. So the non-sphericity of sectors models.
This was GRT paper that was your colleague.
Sorry?
This was GRT paper?
Yes.
Jekara's,
Yes.
yeah.
2000.
On averaging.
Yes. Well, we in a paper we published in 2011, with Boleiko and I, we extended this demonstration because what he did in that GRG paper was only one case. We proved that it's valid for all cases. Okay, so try the following task then. Find a weight factor so that the average of scalars common to FLRW satisfy, well, it's the same thing. We are trying to see if we can describe the dynamics of sectors models in the same way that we've described the dynamics of LTV models, and it turns out that it's possible. We define the fluctuations, and this is the same thing we've done for LTV models. So the dynamics of the sectors models is completely determined by the averages and the fluctuations, just as it happens in LTV models, except that in sectors models, these fluctuations will depend on all the coordinates because R, H, and K depend on all coordinates. Even if the averages only depend on TR, but the local quantities depend on all coordinates. So fluctuations depend on all coordinates. Yep. So the idea is a sort of perturbation formalism in which the FLR background is defined by averaging, and the perturbations are fluctuations over these averages. Right? It's the same thing. The result is encouraging. For example, we This is the same as in LTV models. The shear scalar, the shear tensor, is essentially the fluctuation, this fluctuation, which is what we call capital D. And the psi2 thing is also a fluctuation. This is very similar. See, now evolution equations have this form, okay, and purely algebraic constraints. See, what happens is we obtain exactly the same equations that we had for LTV models, exactly the same. The constraints are also the same. So where's the difference? In the initial conditions. The difference is in the initial conditions, right? That's where you distinguish Sekeres and LTV. See, because, why in the initial conditions? Because the fluctuations depend on the three spatial coordinates, right? And so you have to give that information here. These fluctuations, these are time derivatives, but remember that all these constraints have to be satisfied at the initial slice. And this is where you put the information on the non-sphericity, at the level of initial conditions. But once you put this information, then the Sekeres model, now, again,
solution would be different, no?
it will be, of course. In the LTV case, it's only the radial axis.
Radial, yeah.
Yeah. You have to provide a partition of values of the radial axis. But now you also have a dependence on theta, in different angles, and a dependence on phi.
Yeah.
So suppose that you provide 50 values or 20 values, radial values. You don't have to provide so many values in the angle. Let's say 5 and 5. So how many points you have to provide? In LTV it would be 10 only. Now it's 10 times 5, 50, times 5, 250. So you have to provide much more initial points. And then you will see how, you see numerically how you have this angular dependence once you plot these things. So, but the dynamics otherwise is very similar to LTV, okay? So these are the FLRW evolution equations for the background. For the Q scalars are mimicking FLRW scalars. And these are the evolution equation of the perturbations. And these are the FLRW equations as well. These are very similar to this and this mimic FLRW equations. And these ones, they mimic they generalize, as I mentioned before, the linear perturbations. It's the same, okay? They also provide a generalization of linear perturbations, okay? So, perturbation formalism, I'm going to go very fast. Don't worry about it, not important. Okay. Interpretation, well, we've seen this, the same thing. Not going to repeat the same thing as LTV.
Sir, how much time do you need about?
Half an hour.
Okay.
This is important.
Yeah, you complete.
Yeah, to finish.
After half an hour, I have to distribute certificate.
Okay.
Half an hour.
But like half an hour.
Yeah,
half an hour more.
No problem.
Okay. So this is the same, except that we'll see something about the fact that the three-dimensional surface orthogonal to the four velocity do not satisfy spherical symmetry. See, there are not spherically symmetric hypersurfaces because there is no spherical symmetry. But they can still be foliated, that is, they can still be described by a collection of two spheres. But we will see something very interesting about the two spheres. See? Okay, this we've seen. Now, the surfaces of constant R are also two spheres. However, there is a difference. See, here, notice, this is a metric. So what happens if we set dt dr equals 0? If we set dt dr equals 0, this metric reduces to this. And this is the metric of a two-sphere. So the surface of constant small r are also two spheres. So you say, well, then what's the difference with spherical symmetry? And the difference is as follows. The non-sphericity is the way in which these spheres fill up the space. If we compute the proper radial length, the proper radial length is a proper length among the curves in which r is varying, right? The radial rays.
Sir,
Yeah.
what is actually meant by foliate?
Foliation.
Yeah, foliate.
Three-dimensional space and planes. See, the x, y, z, okay? So you take the planes z equals constant, right? And the collection of all these planes will fill up the three-dimensional space. So this is a foliation on z, right? The coordinate z equal constant, but arbitrary constant, will give you a continuous foliation of R3. Okay, that's the meaning of foliation. So here we have a three-dimensional space that is parameterized by three coordinates, r, theta, and phi. So you can foliate this by r. Each r equal constant is a two space that will be foliating your three-dimensional space. Just as the z coordinate will foliate the R3 space, okay?
It means like spanning the space.
Or maybe
Yeah, but spanning is not a good term because spanning is used for vectors.
Yeah, actually, not in the mathematical sense.
No.
Filling up.
It's filling up. It's a pie. Like here.
means I think if you give example of means packet of bread.
Yes, the slices.
Cut slice of bread.
Yes, you have a yes, exactly. You take slices. Well, of course, an infinite number of slices. Each slice is infinitely thin. But yes, it's slicing the space-time or the space. If you slice the space-time, then you get a collection of three-dimensional. Now, if you have a three-dimensional space, you slice it in two dimensions. Okay? So, in spherical symmetry, what we have is that GRR for a fixed time, GRR is independent of the angles. Therefore, in spherical symmetry, all these spheres that are foliating the three-dimensional space are concentric because the proper length from here to here is the proper length is independent of the angles, right? The same proper length here, then here, then here, then here, because this metric does not depend on R. So in spherical symmetry, the foliation by two spheres is by concentric two spheres, right? Now what happens in Sekeres? In Sekeres, this quantity depends on theta and r. Therefore, the foliation here, the radial length, the proper length depends strongly on the angles, right? So in Sekeres geometry, this foliation is by non-concentric spheres because the proper length will depend on the angles. One way of thinking is that Sekeres models are like spherical symmetry after 4 drinks of vodka.
But sir, they are still sphere, no?
Eh? Yeah, each one of them is a two-sphere. But you pile up the two spheres in such a way that they are not concentric, right? And so this gives you an idea of how Sekeres models deform spherical symmetry, right? Look at this, have 4 drinks of vodka and you start seeing this. Okay, so now, nice result. First nice result is that, remember I told you that you could fit the CMB observations with an LTV model only if you are at the center. But the center is a very privileged position. Now the first nice result with Sekeres geometry is that if you take a chunk, a spherical chunk of Sekeres models, now you have at least 2 privileged observers. Rather than 1, now you have 2. So it becomes more subtle. It becomes more interesting because, see, in the quasi-spherical, okay, let's see which ones, see. So, suppose that you take a chunk of 250 megaparsecs, right, of spherical symmetry. So, the center of all these non-concentric spheres, it's interesting because that's where the shear tensor vanishes. This is a locally isotropic observer. But this is not the only privileged point in this chunk, because you also have the geometric center. In spherical symmetry, the geometric center is the same as the center of all the spheres. Right? But here it's not. In Sekhar's models it's not. So you have two privileged observers, right? This means that you could fit CMB observations if you are very near here. But if you are very near here, you can always choose the spherical, you can always choose the Sekhar's model so that this place of the locally isotropic observer can be anywhere. And in fact, as the Sekhar's model evolves, the position of this place will also be changing around. So this makes the models, this horrible problem with spherical symmetry, that in spherical symmetry that doesn't happen. In spherical symmetry, this and this coincide and stay put all the time. They don't move around. So to fit CMB observations, you have to declare that we have to be there very near. But in Sekhar's models, we could be, for example, here, and this point will move, and we can be very near this point, but very far from this one. So our location in a Sekhar's model to fit the CMB is no longer so unique. It is. It adds more complexity.
Means you can give rotation to whole this diagram as a whole.
No, that's not the point. No, the point is that we have two privileged observers instead of one. Therefore, you can, if you are one, then you can be close to the other one. And if you are close to one, you can be far from the other. That means that your position is not unique.
Yeah,
in spherical symmetry, these two are the same and stay put. Therefore, to fit the CMB, you have to be here. If you are here, then you are in a very bad position.
No, I am not telling that thing, but if you will rotate the whole diagram, then what will happen? That will go up, so there you can observe.
No, but you can't rotate the thing because there's no spherical symmetry. If you rotate this, then you get a completely different model. It's not equivalent. If it was spherical symmetry, then you can rotate this thing and it remains the same. It doesn't matter. Everything is invariant under this rotation. But here, no. If you rotate this thing, then you are in a completely different model. What happens is that in spherical symmetry, either you are here, very near, or you don't fit CMB observations. In a Sekhar's model, because this thing will be shifting, then you can be here and fit observations. You can be here. The chances for your location to satisfy CMB constraints increase enormously. You can be in many places where CMB observations are going to be fit. You don't have to be only in one place.
Because, sir, no matter where you are, you could always choose a sphere at which you are the center of it.
No, also no, not true. No. Where did you get this idea? Not true, no. The position of this point is given by the model. It's not arbitrary. It's arbitrary at an initial slice, initial time, but then it will be moving. No, this thing will be moving around. You cannot say at a given time to declare by decree that, no, it depends on the model.
So as time change, the center may be changed, na?
Yes, well this will remain fixed, but this will be moving.
Yeah, to what I am telling you.
This will be, but not rotating.
Not
it will be
rotating.
moving.
It's moving, yeah.
It will be moving around, depends on the model. But your chances to be in a position where the CMB is satisfied increase 1,000,000-fold in compared with LTV models. Because in LTV models, there is no dynamics. Either you are here, if you are anywhere else, then you don't fit CMB observation.
Sir, you took a dipole and you got two positions. So why not take a multipole and...
No, because why not? Well, show me and I'll be eternally grateful. Show me and I'll be, because that's what the solutions allow you.
Because then we can fit CMB
No,
everywhere.
if you are able to present a quadrupole solution that generalizes Sekeres, I'll be eternally grateful. I'll build a monument for you. It doesn't exist. It's not possible. No? Solutions don't, numerically maybe. Yeah, why don't you choose them? Of course, if I could choose it, it would be stupid not to choose it. If I had a quadrupole at my disposal, why should I stay with a dipole? But this is as far as you can go with exact solutions, right?
This is the most...
This is the most general. If it is exact, numerically you might get, but this has to, this requires non-trivial numerical methods, right? So it's not that I'm not showing and keeping an ass under my sleeve. They say these are dumb guys, only going to show them the dipole, keep the quadrupole for me. No, I don't have it. I don't have a quadrupole. Okay, I'll show you how to mimic a quadrupole very soon. Okay, before Sushant gets very.
No, I want to.
No, because you want to.
I want
to listen.
Because
Okay.
the only question is, the only thing is, cell crossing we are avoiding. Is it assumption? Isn't an assumption?
No, shell crossing is like LTV.
Yeah,
You
but
can
we
find
are
conditions.
assumption.
No, you can find conditions where shell
I
crossings can be avoided,
R dash is greater than. That's what we are doing here.
but they can arise.
Yeah, they can arise. Yeah, that's what I. Is an
Okay.
assumption.
Now, Sekeres model defines a precise direction in 3D. See, I was telling you
Yeah.
that this dipole is moving. So how do we find the direction which is moving? Well, let's look what happens in, let's take one of these spheres of constant radius, constant small r, right? And if we make this condition, we look at the angular extrema. This is the extrema of the extremum of the dipole, but only in the angular directions. So we solve these two equations, and these equations have the following solution. And this is very nice because it determines a curve. It determines a curve that we call the curve of angular extrema, and it is as follows. See, this is a projection into the equator. This is a sphere of constant r. And then the solution of this system will determine a curve. So what's the meaning of this curve? It means that, for example, this curve, for each one of these two spheres, we have a direction. See, if you fix r, here we're fixing r, it gives you this direction and this direction. This is the angular maxima will be here. The maximum, see, this is a two-sphere, right? For this two-sphere, this curve assigns one direction and another direction, right? But this shows you how your choice of parameters will tell you how the dipole direction in each one of these two spheres. So this is how we can assign directions to the dipole, by the choice of the functions x, y, and z. Now, important particular case, axial symmetry. What happens in axial symmetry? Axial symmetry is when you have a unique direction of the dipole, the axis. So in axial symmetry, you have invariance under rotations of this type. Here we don't have rotating matter. It's just that the distribution of densities or anything is such that it is invariant under rotations along an equator, for example. Now, what would be the dipole to get this? here we would need the Sekerres dipole to point in a single direction. And then we would get axial symmetry. So in this case, this is like demanding that these angles, these are the angles of the dipole, remain constant. And the solution of this system is that the three dipole functions have to be proportional to the same function. And these constants here are going to tell you the orientation of the dipole for the axially symmetric case, right? This is important because, see, what we have here is that if we choose our parameters in this way, then these constants determine the direction of the axially symmetric case. So we will have invariance under rotations of this type, okay? Because this is an axially symmetric Sekerres model, right? Okay? And we obtain it by fixing our parameters x, y, and z in such a way that they are proportional to one single function, and the constants here are the ones that determine this angle, okay? But this is a single dipole, only one dipole that determines axial symmetry, right? The general case, we wouldn't have this because the angles will be changing from sphere to sphere. What we're demanding is that the angles remain constant for all the sphere, and this defines a single axis, right? Okay? Now, very important what follows. Very nice, but you said you were going to show us how to model structure. So far, we've seen lots of mathematics. So how, okay, fair enough, good question. So let's put down, let's put our feet back to earth, okay? Now, okay, early work on Sekerres models explored basically axially symmetric cases. And what this early work showed is that the simple dipole arrangement, axial symmetry, yeah, allows you to describe two structures, an overdensity and a void, along an axial dipole. The overdensity and void correspond to a maximum and minimum of the density, and they move with respect to a commutative phase. So what happens is, in spherical symmetry, we can only describe one structure, either an overdensity or an underdensity. So what happens if we take a Sekerres model that is a dipole? So then we can describe two. Instead of one, we can now describe two. What will happen is that one will be at r equals 1, and at the other point, let's say you have a void, and then next to the void you would have an overdensity. They are all distributed along the axis of the dipole. This is what happens with Sekerres models, very simple Sekerres models in which you have axial symmetry, okay? And this is all the early work, this is practically all work done in Sekerres has been in this direction. So people assume, they tell you, yeah, with Sekerres models, the only advantage is that you can describe two structures instead of one. Big deal. And that's what people think. And this is most of the early work on Sekerres models. In fact, what you have is something of this type. See, this is early work on Sekerres models. You have, this is the axis of the dipole, and there is axial symmetry, and what you have is an overdensity next to a void. Overdensity next to a void, and this would be the profile. This would be the density profile, the overdensity and the void. And you can show you can have probably one case in which you have two overdensities and one void. But now the density contrast is changing on time. This is a curve of this configuration at different times. So you can see that the overdensity becomes, the density contrast becomes larger, and the void becomes deeper. This is density contrast. So it changes on time, but essentially the dipole, this very simple dipole in axial symmetry, will allow you to put one, maybe, to put two, maybe three overdensity structures in the dipole direction, right? So that's it. So that's what people used to believe. And in fact, most people still do that. I'm not going to be bragging, but except for my papers, all Sekerres models are constrained in this way. There's nothing more with them. Now, in 2011, my colleague Boleiko and I, we tried to improve this situation, to put more structures. And what we did, it was published in Physics Letters B, 2011. What we did was to construct a Sekerres model in which had 11 structures. Not 2 or 3, but 11 structures. And we place them in different positions. So what we have is a collection of elongated overdensities and voids around the central void. This is a cross-section, a tessellation at the equator, right? So we had something like this. You can see the density contrast, and it was nice. In fact, it was published. Well, it had some errors. That first, we did not do it systematically. We did it by trial and error without understanding, and we used density distribution with step discontinuities. This was the main objection by the referee. The referee said, no, density is not continuous. This is just an approximated solution. It's not an exact solution. So we had to take that into consideration. But it was the first time that a Sekerres model was used to describe more than 3 structures, right? So it was published here. And we were playing with the parameters, really didn't know how to do it, but it happened, and so it gave rise to a small letter paper, right? So, I'm going to show you now how can this be done correctly. And not only 11, you can represent how many you want.
10.
10? Nothing.
N.
N's, you can 758 structures. Yeah. Yes, we can. And we can place them, and you tell me, I want 758 structures, and I want them here. I can place them there. Perhaps there will be some of them might not be able to place exactly in that position, but nearby, I can place them. Right? And now we know. Now I know how to do that. But in 2011, I'm just playing around. Now we know how. Okay, so to show you how, let's concentrate on the density, because the structures themselves are defined by the density maximum. See, if there's going to be an overdense region here, I identify it by a density maximum here. If there's going to be a lower density here, I identify it by a density minimum here, right? This is what defines the structures, the maxima and minima of the density. So let's concentrate on the density, right? So let's concentrate on the density, define overdensity with maximum, density void with a minimum, and a transition, it's a saddle. Transition from minimum to maximum, necessarily a saddle, or a saddle-like one. So the task is to manipulate the free parameters so that we can locate the density extrema in assorted positions, wherever we want. The idea is that I locate the structures by locating the extrema of the density. That's the whole trick. That's the whole thing. Now, for this purpose, we have to solve this equation, because this is the equation that gives us the spatial extrema at an arbitrary fixed time. Now, what we will see is that we solve this equation, we get the extrema, but the extrema will not be in the same place. It will be shifting on time. The position of the extrema shifts on time. But nevertheless, this can be solved, and the location of the extrema will shift in time, which means that the overdensities are not comoving, they have peculiar velocities, which is realistic, right? small peculiar velocities. Peculiar velocities are velocities with respect to the comoving frame. So this is realistic. And then the nature of the extrema, whether it's a maximum, minimum, or saddle, is found by the second derivatives, which is the Hessian matrix of this system, right? So you can look at the conditions. Now, what happens in spherical? Okay, so people might be asking, why this is not possible with spherical symmetry? Why with spherical symmetry we cannot represent 758 structures? We can only represent one. I'll explain why. Spherical symmetry, the origin of spherical symmetry is always an extremum. It is either a maximum, an overdense region. That's either the density reaches a maximum at the center, or it reaches a minimum. It cannot be a saddle, right? Well, if regularity conditions hold, the center is either a maximum density or minimum density. But any other point, and so it's a proper extremum. It's an extremum that is either maximum or minimum. But any other point outside of the center cannot be a maximum or a minimum. It is necessarily a saddle. And I'm going to show why. See? Okay, these are the conditions for a maximum at r equals 0 and a mean central over density central board. So, if regularity conditions hold, then this is the only proper extremum in spherical symmetry. So, suppose that this is your density profile, right? Your density profile tells you there is an underdensity here, but you can say, well, what happens if I do my density profile like this? Wouldn't I have a maximum here? And the question is that you would have a maximum of the radial profile, but not of the three-dimensional density. Three-dimensional density would behave like this. Here is your minimum central, but then all these bumps that you do in your radial profile is really defining spherical shells of higher density and lower density. It's not defining a structure, right? Not understood.
Yeah, understood.
Maybe you can explain to me. Very easy. This is a representation of what happens in the equatorial plane, right? So this is the density, the radial profile only. But this gives information on the radial direction. But what happens in the angles? Because of spherical symmetry, what this radial profile has to be repeated in every angle. No?
Yes.
Yeah. So if you repeat this in every angle, then necessarily, if you do it in this angle, then you get density increases, right? Density is increasing here in this angle. But then because of spherical symmetry, exactly the same thing has to happen in every angle. So what you get is not really a structure, but you get a spherical shell where the density is high, right? And this is what happens here. This is represented here. In every direction that you move, you see this profile replicated, right? So it's not really a structure, it's really a shell with high density or low density, see? It's a compression or non-compression shell, spherical shell. This is what you get with spherical symmetry. Now, why can we model structures in centers and not in LT? Because this is what we get in spherical symmetry. The condition r prime equals 0 for r greater than 0 does not mark a maximum or minimum, but a spherical shell that is overdense or underdense, because all directions are equivalent. See, even if we have a bump of the radial profile, because this bump has to be replicated in all directions, this is what we see. This is the projection in the equator of the density, right? So the only what we have here is only a minimum, which is the real extrema is here. Here what we have is a sort of saddle, even though r prime is greater than 0, but r prime is only the radial profile. The radial profile does not tell you the full information. And because of spherical symmetry, the radial profile has to be replicated in all directions. Now, what happens with Zacharias? Because of the angular dependence, then this profile need not be replicated in all directions, and you can choose it so that it is replicated with different intensities in different radiations, so it will allow you to describe a second extremum here, right? And this is why you need angular dependence to describe many structures. Spherical symmetry is not possible, only one. And shells, underdense, overdense shells. Here, the overdense shell actually becomes an overdensity because you can force an angular maximum here. Here there is no angular maximum. Here, because there is no angular dependence. Here, because there is angular dependence, you can force the coincidence of a radial and an angular maximum. And that is why we generate an overdensity. Okay? So that's the trick. That is the trick. So program to follow. First, compute the angular extrema. We want to know where, in which angles we have an extremum of the density. Then we compute, what we can show is that the angular extrema of the density are the same as the angular extrema of the dipole. So this is very important because once we select the parameters that give us the location of the angular extrema, we will know that in this angle, we will know that for this sphere, in this angle, the density will have an extremum in this direction, right? So we know that the density will have extrema in this direction. This is a necessary condition. So this is what happens, for example, this is in the case, this case is not a dipole, because for the dipole, all the directions will have to, I mean, this is not axial symmetry, right? This is a dipole that is changing direction for each other. This is what the opacities and voids must be located along the blue curve, and the saddles along the red one. Anyway, we have to what we need to do is first to locate the angular position of the overdensity. Forget about the details, but this is what we need to do. How can we obtain a precise location of the structures? We define the dipole parameter as piecewise functions. See? This is an axial dipole. Very simple, right? Here, what we would know is that the structures would be located here, right? This is what people do, axial symmetry. In axial symmetry, the functions are defined in this way. So there is a single direction for all the spheres, and structures will be located in this direction. Now what happens if we define these functions as, these parameters as, remember that these angles at A0, B0, C0 tell us the exact direction, right? So the direction depends on these constants. Now we define these parameters in a piecewise manner, in this way. What do we get? We get that once we will get this, here will be one structure, here will be another, and we can choose where to place the structure by choosing these constants, right? By choosing these constants here, in a piecewise manner, that this function takes this form, in this radius, this form, the following radius, this form, the following radius, etc., etc. So we can locate them everywhere in different radial and angular ranges by choosing them like this. So we can put the structures in a sort of in this way, right? This is the trick.
So the constants are arbitrary.
Yeah, that depends where you want. The constants relate to the angles. If you want the nth, the fifth or the sixth structure to be located at an angle 30 degrees and 45 degrees, then you choose your constants accordingly. And the formula that was shown before, that relates the angles with the constants. It depends where you want to place it. You choose the radial interval, and then the constants will tell you the direction where the structure will be looking. Okay, that's the way to do it. Now, overdensities and voids can be placed in arbitrary locations by this manner. So notice that what we're doing is there is a single dipole. Now, what we do is that we put little dipoles in different radial ranges, right? So this is one way in which we can construct multipoles by superposing many small dipoles, right? See? We superpose many small dipoles in different directions, and this creates a multipole. This is the trick. Sakhar's models only allow dipoles, but who tells us that the dipole has to be of infinite extent? If we do that, then we get only two structures. Now, what we do is we take this dipole, we slice it into many pieces, we put the little pieces in this part, right? So, in each small dipole, we have a structure. And this collection of small dipoles is what reproduces the multipoles. This is the trick. You know the trick. Now you can sell it somewhere. Do your startup company, produce cosmic structures, and sell them.
So means with this you can also explain structure formation, no?
Yeah, that's the idea. Of course, note there are limitations.
But still, yeah.
But look, it's an exact solution.
Yeah.
Except that we are treating it in a piecewise manner, and it can be still refined because so far we have one structure in each radial region. We can put n structures in the same by doing also angular partitions. So far,
and then
that was what I was thinking. I mean, only one
that's the
structure
next. Yeah, so far only one structure in each radial shell. But that's not all. Now we haven't finished.
It's similar like magnetic domains.
Sorry?
The magnetic domains. A big bar magnet, you have two dipoles.
Yeah, okay,
small
that's a
dipoles.
good analogy because the magnetic dipole. Take little magnet here, little magnet here, little magnet, and the electric field, the electromagnetic field will be of a multiple nature, right? That's superposing many small dipoles, you can reproduce a multipole. So that's the trick.
And then from observations, when you get data, you can match
Yes, of
this
course.
theoretical work can be matched.
Yes, that's the idea. See, spherical symmetry, zero dipole, one structure, monopole, W equals 0.
We have to go there also.
No, wait, this is very important, please.
2 hours take.
Eh?
2 hours for travel.
Yeah, but this is very important. This is very important. More important than these people can wait. Sorry, they can wait. This is very important. I'm sorry. This is very important. Now,
But we can. Anyway, it's fine.
we can get there late. They're not going to. Nothing is going to happen. Now, spherical symmetry. Sorry, Mexican time. Mexican time is very elastic. Now, zero dipole, spherical symmetry, one structure. We're about to finish, not far. Simple dipole, axial symmetry, two structures, same W for all coordinates. Simple structure, axial symmetry, two structures, right? Now, here, radial, piecewise, we do radial partition, and so we have one structure at each radial range. This is as far as I've seen. But then the point is that all you can do? No, of course not. We can do angular partitions in each area here. We can do angular partitions and position an arbitrary number of structures in each, well, arbitrary, if we put too many structures, they will be too packed with each other. But a reasonable number of structures, like we can also put. And so, not far from the end, it's already missing. See? We are still missing the radial derivative. How do we know there is a radial maximum, minimum? Well, we take this thing here, the density along the dipole, and we notice that this is the formula of the density along each one of these small dipoles, right? It has this form. And we see here that the denominator has this is the gamma, the same gamma we had in LTV models. So we keep this thing greater than 0, but we make it very close to 0. So what would happen with the density? It would grow a lot without diverging. If this is 0, then it's a shell crossing. But we keep it very close to a shell crossing without allowing it to reach the shell crossing. So the density will grow a lot. And this is a sufficient condition for obtaining, we do this, we get this behavior. This is a sufficient condition to guarantee that there is a density maximum. Then another technique is, well, this is another technique. What we do is we assume that there is boundaries of local homogeneity, only in a boundary. That's technical thing, don't worry. Yeah, let's skip this thing. Then what we obtain, we're about to finish. What this obtained is a very good coarse grain approximation of the density contrast. See? This is what we obtain. This is the type of description that we obtain. This is density contrast, right? So with what are we comparing this? With this. This is a reproduction of the Laniakea group of galaxies. This is the mother of all the superclusters, right? And this is a density contrast map. There's a local void, and we are somewhere here in this area. See, I think we're here, Milky Way is here. So how can we relate this to this? Well, we can take an overdensity here, an underdensity here, overdensity here, void area here, void. Now this is a coarse grain description. It's not, we're losing detail. Impossible not to lose detail. We're dealing with an exact solution. All these numerical solutions, they use supercomputers and heavy artillery of computer. We're just using an exact solution. Numerically we have to do it, but simple numerical. Yet what they do is Newtonian. It's 300 years old physics. And here is fully relativistic, only 100 years old physics. So that's a nice thing. For example, this is the Hubble scalar. The Hubble scalar is larger in the areas of low density, right? The Hubble scalar. And these are the, this is also the Hubble scalar, and this is the density contrast. This is low density, high expansion. High density, low expansion, which is what is expected. And we can compare this with this velocity. These are reconstructions of the velocity field. We can compare this with this. Again, it's coarse grained, but it's infinitely better than spherical symmetry. Okay? Then, coarse grain, for example, we take this is a three-dimensional projection of numerical simulations. Well, this is what we have. This is also a coarse grain approximation of this, right? Which we'll never get with spherical symmetry. And of course, we're never going to get the detail that these people get. However, it's an exact solution. And then, peculiar velocity field. We can, this is the regions of high velocity and low velocity. regions of high velocity and low velocity. So we can also reproduce velocity fields in a coarse-grained manner. And then finally, peculiar velocities with respect to the center of the void. This is what we obtain, and this is the experimental data. Experimental data says that peculiar velocities roughly increase linearly with respect to the center of the local void, and this is exactly what we obtain, and in fact, here we get, and we reproduce the numerical values of these peculiar velocities. And, well, conclusions. Something that people might ask is, do you always need to have a sort of central void? And the question is no, we can sort of remove that, but that causes certain problems. But at least, we cannot describe the whole universe with this, but we can describe a large chunk of the universe, right? Because, yeah, we have a sort of a spheroidal void in the center, and then we have elongated structures. They are elongated, and we can control how wide they extend. We can have certain control on them, but this is of course not perfect. This is just much better than what can be done, and its utility, especially for structures in the range between 20, 30 megaparsecs and 200, 300 megaparsecs. We don't know how good it is for larger illustrations. So the conclusions. We have shown how effective coarse-grained modeling can be achieved with Secher's models. We have shown how the angular extremes of the dipole function determine the orientation at each surface and determine the angular extreme of covariant shore. We have shown how maximum and minimum of the density can be located in assorted positions in spherical coordinate system. So we can model non-trivial distributions of cold dark matter, and so the potential for applications of this is enormous, right? And so that, I think that I conclude here. So otherwise, Sushant will come with a sticker.